my pleasure to introduce Frédéric Chyzak to speak on generalized Hermite reduction, creative telescoping, and definite integration of D-Finite functions.
Thank you, and let me thank the organizers for inviting me. It's my first time in that, and a nice surprise. Okay, so it's about a work on in computer algebra about integration algorithms to symbolically compute parametrized integrals, and it was done with colleagues in France, Bostan, Lairez, and Salvy. Okay, so you've heard the title. I'll first briefly define the. It was working. It was. Okay, so what are integrals? What is my goal? So my goal is to automate the proof or justification of such identities, or the discovery of such identities, where we have integrals of special functions given by names, Bessel functions, or families of orthogonal polynomials like the T's, that is, or the H for Hermite. Okay, so there's a variety of applications here, single sums, multiple sums, but each time a variable remains, and this is the kind of integrals that I'm interested in. And just the last one is a case of a computation of a diagonal or a residue, and it's related to a talk with, it's the same, for the same kind of applications as the talk that we heard yesterday. So to some extent, what I'm presenting here is algorithms and methods to perform the so-called creative telescoping that was mentioned yesterday in Christoph's talk. So the next term I wanted to explain is creative telescoping, which in essence is a method that was brought to computer algebra by Zellweger in the 80s and 90s, and that performs by differentiating under the integral sign. And here is one example, that very simple example that you could do by other means, obviously. But suppose you want to compute this integral here of a function of two variables, and the integral is parametrized by this b. So an approach, a possible approach, is to take the derivative with regard to the parameter of the integral, and then perform some integration by parts. And these boundary terms here, they cancel, and you can relate the remaining integral to the original integral. And if you look at what has happened on the level of the function, that is disregarding the integral signs, you identify such an identity here. That is, the two terms here form this recombination of the function and its derivative, and what is hidden there is that it's a derivative with regard to the integration variable of an auxiliary function that is again related to the function to be integrated. And if you discover this, or if some algorithm provides you with such an identity here, just integrating with regard to x from -infinity to infinity delivers you here an expression in terms of your wanted integral, and here boundary terms that in this case happen to be 0. So in this case, it delivers you a homogeneous differential equation on your parametrized integral. So the talk really is about several methods and optimizations of methods to obtain this bottleneck, this relation. Okay, so it's about Hermite reduction. Hermite reduction, you know, of course. It's a method that allows you to reduce the pole order by some sort of Bézout relation here about the numerator. Okay, it's Hermite, and I say Hermite, but really it was discovered by Professor 30, 40 years before Hermite. Okay, and the last term I need to introduce is differentiably finite functions, or D-Finite functions. And really, it is the observation that when dealing with special functions, the linear differential equations are the right data structure to perform algorithms. So, given special functions, you can have a database of equations they satisfy. You can have those equations as their definition. We have algorithms in computer algebra to solve linear differential equation in terms of special functions. So large classes also fall, the large class of algebraic equations also falls under this paradigm. And when you have differential equations, you can, for various functions, you can recombine them to get equations for products, sums, expressions in special functions. So what I'd be interested in today is the case of definite sums and integrals, well, with the focus on integrals. And for such method to apply well, we restrict to differentially finite functions, which are those functions that that have a linear differential equation, or in other words, those functions whose derivatives, whose infinite set of derivatives, only span a finite dimensional vector space over the rational function field. Okay, so this is for the univariate setting, and obviously, as I'm interested in parametrized definite integrals, I need multivariate objects. So we define also multivariate differentially finite functions as those functions, here are 3 variables, whose infinite set of all cross derivatives span a finite dimensional vector space. And a generalization of this is in terms of what we've called D-Finite. That's just if you have shifts and differential operators and the like, then you imagine the definition that the natural vector space is only finite dimension. Okay. So I'll go now a bit deeper in this notion of creative telescoping, introducing the notion. So it's something that appeared first for sums and has an analog for integrals, and I'll focus on this one, but the name comes from the summation case. So really, given a function to integrate of two variables here, to integrate with regard to x, suppose we have such a relation, and again, what is it? It's that on the left, it's a linear combination of the derivatives with regard to the remaining parameter with coefficients that only involve this parameter. Here these are rational functions. And suppose you have a relation of this type that is equal, or an expression of this type that is equal to the derivative with regard to the integration parameter of some auxiliary function, then, as in the example I've given, you can integrate and obtain a relation for your integral of interest. So here I've written often. It's often 0. So I suppose it's not 0. We have tools to kill it. Just that you increase the order of this relation here. So in principle, you can think that you have a homogeneous differential equation. Okay. And for the rest of the talk, and as is done in the literature, I'll call the blue part, the underlying operator, the telescoper, and the auxiliary function here, I'll call the certificate of the relation. Okay, so there's been a huge literature on creative telescoping. I'm afraid you can't read this, but it started in the 40s, and as I said already, it entered computer algebra in the 80s, 90s, and since then it's been a continuous work. And why? Because what I've suggested is just a method. And to make it an algorithm, you have to determine if you want to work for first order equations, higher order equations that define your input, or if you work with differential equations or shift analogs or Q analogs, or like mixed case or only differential case. You need. There have been works that go beyond this constraint of finiteness of the vector space that defines the function, and also you see in this equation here, after integration, this goes to 0. So to some extent, the certificate is just an intermediate object if you want to obtain only the blue thing. So there has been work to compute with or without the certificate. And also various approaches, ranging from just linear algebra or solving auxiliary functional equations, or doing non-commutative derivative bases, or, and this will be the topic of the talk today, reduction of singularity of the rational functions appearing in the calculations. Okay, so I've said already, I just named two names. So one is Zyberger, who introduced the topic to us. And the second is Chen, who initiated this shift to this new method starting around 2010. Okay, my goal now is to show you the evolution of those algorithms, the evolution of ideas, always using the same running example. And this example is the integral of a variation around Chebyshev polynomials, about the sequence of Chebyshev polynomials. So it will be integration with regard to x, and n will remain as a parameter, and here it's a shift parameter. And the p that appears here will be a differential parameter. So we're interested in the integral from -1 to 1 of this, and in a way that we can prove that this integral equals this variant of the Bessel function evaluated at p. Okay. So, as I said, each of the blocks here, an exponential, satisfies order 1 equations. The Chebyshev polynomials here, they are known to satisfy second order equations. It's an algebraic term, it's first order. So there are algorithms that can multiply these in general, in the sense of multiplying systems of equations, systems of defining equations, so as to obtain here a second order differential system, actually a mixed differential different system. Here you have a second order differential equation. Here you can rewrite the first shift in terms of derivative with regard to x, and here the derivative with regard to p is related to to the function itself. Okay, so this will be our input as obtained by other algorithms. And okay, I want to have a more compact notation, so I'll use, as is customary, the index to refer to either derivatives or shifts, or iterated derivatives or shifts. So now the equations are more compact, and this system really is, in my view, a derivative basis. So this can be made formal. And what it means really is that you can use all such equations in an oriented way, so that you can rewrite any second order derivative with respect to x as lower order terms, any shift in n as lower order terms, any derivative in p as lower order terms, so that an observation is that any iterated shift or derivative of the function can be rewritten as a linear combination of those two guys, the f and its first derivative with regard to x. Okay, so now what is our need for creative telescoping? We need to obtain such an equation here that's some linear combination of those shifts of derivatives, not using derivation with regard to x, with coefficients that only depend on the remaining parameters n and p here. And this has to be a derivative with regard to x, the integration variable, of such an expression here. That is the choice in the algorithms here is that this auxiliary function g will be searched for in the expressions that you can obtain linearly from f after applying those shifts and derivatives. And as we've observed here, any such expression can be condensed as, or rewritten as just a linear combination of f and its first derivative in x. So we'll give algorithms to get this. Okay, so my goal is to present you an algorithm that uses an extension of Hermite reduction. But I like to view this as an evolution, that is to explain it in comparison to what we did before that. And so don't feel it's just a talk about me, myself, and I. But it happened by coincidence that the algorithms I'm comparing I've worked on them. Okay, so again, here is our input. And this input, I said, we want to view it in this diagrammatic way. So here it's an often that you, okay, so the shift, the order of shifts goes up, and it's like, okay, the two arrows are pointing to you. So what it means here is that this orange box contains the two green blobs. These are the two basis elements here. And anything that is above, which means closer to you, from those three orange blobs can be rewritten down to the green. And now the special form of creative telescoping relation that we're looking at here involves only those blue points that are on this left face of the orthogon. Okay, and an algorithm is you target some order for the equations you want to get on the integral. That is the total order with regard to shifts in n and derivations in p. And so it's first stated as a method. You think you iterate for higher and higher targeted orders. So for r is 1, 2, etc. Until you find something. You try and solve this for undetermined coefficients here, the c's, that are rational functions in n and p, and the a and b that are rational functions in one more variable, namely the x here. So what happened? Okay, I just expanded the derivative. We know that we can reduce for any given concrete r, say r is 5, and then given the u and v, you can rewrite this derivative here as some linear combination of f and fx. So after expansion, you can write this here with the same unknowns. I've applied the derivative here, so I've written the relation, the wanted relation, in terms of this basis element f and fx, from which we get relations on the a, b, and c's that we want to solve for. And these relations are first order with regard to the duration in x, and they're linear in the c's. So you can obviously do some sort of elimination and obtain a single equation for the b's, involving only the b's and the c's. And okay, we want to solve for rational functions in x and the n and p. And for this, we have in computer algebra, we have a decision algorithm by Abramov that is able to solve for such rational functions, and a slight variant of it solves for the parameter c's at the same time. So we restate that. So the Abramov's algorithm really is for the case this is known without parameter here. And now what we want is not a rational function that is valid, a rational function b that is valid for any c's. We want to select those c's that allow the existence of the b. So along the algorithm, you look at the constraints and you get linear constraints on the c. Maybe you even find the right c's such that the b exists. Okay. And once you've solved, you can replace into there to get a. Okay, and on this example, here is what you get. So you don't get already given you the final relations. So the ABCs, there is a set of ABCs for this and a set of ABCs for this one. Okay, so it's an algorithm. Oh, sorry, and then the next step is that I do the integration so that I get those functional equations for my integral, and you recognize either you have an algorithm that solves for expressions in terms of special functions, or you look into tables and you recognize that this here is the equation for vessel I. Okay. Oh, and it's been implemented already long ago, and okay, it won't go into details, but just to say it works in, it's a simple integral, but it works in a fraction of seconds. Okay, so it's an algorithm, but we can see problems in this. And so the first property is that this telescoper is really what we want. And the certificate is just needed because the algorithm proceeds by finding the certificate in order to find the telescoper. And the problem is that this certificate, at least if you expand it, it's really large. So it's large, and you need to compute it before disposing of it. So also, I've suggested an algorithm that works for successive R's, and there's little reuse in the way I've presented it from one R to the next. So it's a lot of a loss of calculations. And just to give you an intuition, I won't quantify the complexity, but how much the certificate is large. So here is an integral. Here it's a double integral that's related to some model of works in combinatorics. In fact, it is a diagonal here, a diagonal calculation. You find something that's okay. I haven't displayed it, but it's simple. It's a small fifth order equation on the diagonal. And it's just 2 kilobytes, just writing, so it's 1 page string to write the telescoping equation that you're interested in. But the intermediate objects here go up to almost a megabyte for nothing. Okay, so, sorry, so, breathe. So, we need another method. And this is what uses Hermite, an approach by Hermite Reduction. So let me go back to the classics. So what is it really, Hermite Reduction? It's to compute a primitive that is not a definite integral, but a primitive. And given such a rational function, the method rewrites by reducing the pole orders to here only order 1 in this Q star, that is the square root part of Q. And there is an already a fully integrated term that is here, that here uses the Q minus, as orders reduced just by 1. And moreover, this A here is confined. It's confined in degree as the numerator of A has degree less than the square root part of Q. And okay, this can be obtained in good complexity because blah blah blah. So we have algorithms in good complexity to perform what is needed. That is a so-called square-free factorization, where from the denominator Q you can isolate factors of each power. And the way to view it, one way to view it at this is that this A here, the A that remains, is the obstruction to the possibility to have this primitive be a rational function. And it's been completely understood. For example, we understand that this A induces logarithmic part in the primitive. This is one. So why not use this? So in just of stopping here, saying, oh, A is not 0, I cannot compute a primitive that is rational. Why not view this A as an abstraction and use and recombine abstractions so as to get something? And this is what we started with the colleagues. First, on bivariate rational functions. So now I'm focusing on such a problem here where P over Q is a rational function, and it's, here I denoted it by a contour integral. It's for example, when you compute a residue or a diagonal or other extractions in combinatorics, it's a natural setting where naturally you don't need the certificate and only want the telescope. So I'm just repeating here Hermite reduction. So the A is confined, but okay, this is how it's presented in books, but now take the derivative of it. And you see that really what it does is that the initial rational function here is rewritten into this nice form with A confined in degree and Q star is smaller, modulo a derivative with regard to x. And now, okay, now remember this idea of creative telescoping. I'm interested in successive derivatives with regard to T of P over Q. So I'll just rename the numerators, giving them an index. And if I take the derivative with regard to T, here's what I get. Okay, I can exchange derivations here, and I'm taking the derivative explicitly here, it goes to order 2. And now I can play the same game on this, that is reduced back to order 1, modulo a derivative with regard to x. And I suppose I reorder the factors, I get this. I get another numerator for this. And okay, see this now, of course, I can continue. I have for each I, that is for each order of a derivation here, I have an expression here. And modulo the derivative of this expression, here I have this polynomial A superscript I that is confined in degree. And so I'm just saying it, but these expressions here, if you expand them, they grow like the certificate, which I've said is too large and we don't want to compute it. So in this calculation, let me go back. So I will distinguish those two plus. Mathematically, it's the same plus, but computationally here, let's consider that this plus really expands and normalizes the polynomials, whereas here the plus, you just consider that you keep the program of calculation. So if you do so, or if you throw away these expressions, you get, without the cost of writing the e's, you get the a's. Okay, and now we use this confinement in degree, which means a confinement in a finite dimensional vector space, so that when you have considered sufficiently many i's, you can get a linear dependency of these polynomials a's with coefficients that are in T only, and whenever those are recombined to 0, you perform the same recombination over the whole expressions, and you get this relation on the function to be computed. And what we could prove is that I won't enter complexity questions here, but we could get a good complexity by being incremental and, as I said already, not expanding the e's. Okay, so this was for the bivariate rational function case, and really my goal now, and I hope I'm not going too fast, no, I'm fine, is that we want to, after this work, there's been a succession of works trying to extend the approach to larger and larger classes of inputs here. And what I'm heading to is to present the algorithm that does the same, performs the same ideas on the large class of differentially finite functions. Okay, so actually, to pass from this bivariate rational function case to what I'm presenting, there are two extensions, two ideas. So one is, okay, we need to extend from rational functions which really satisfy first order differential equations to objects that satisfy higher order equations. It's one thing. And the second is that in this, my view on the literature that has followed this first algorithm is that people have tried to design a reduction process for larger classes of functions. But other D-Finite functions may have rather complicated singularities. You can have logarithms, you can have exponentials, and you have to take this into account if you want to generalize this idea. So here in the work I'm presenting, we have followed another route, and it's all intermediate objects are really expressed as by a set of rational coordinates in terms of the function and its first few derivatives. And instead of trying to do a reduction on the full function, we've designed reductions on these coordinate systems, a set of coordinates. So here is the picture already just for the rational function case. What I've just given on the previous slide is that each t derivative of the rational function, p over q, was reduced to some normal form. So it was the function itself. And now, if we do it a bit differently, is that any successive t derivative of f really is some rational function times f. So this first one is 1. And the new algorithm, what it does really is that it tries to simplify those rational functions here. And we'll show that in a case where there's not only one, but several elements in the basis. Okay. So far, I've avoided these technicalities that I will need now. It's to pass to the operator notation. So, for the rest of of this presentation, I will consider just two parameters, and here by this I denote the algebra of say linear differential operators with regard to x and t, and with coefficients in some rational function field k of t x. I have not said it, but k is of characteristic 0, and let's do k is q. Okay, and this m sub f, it's just the module. I view that as the module generated by f. That is, it's the set of all expressions you can get by applying an operator to f. And okay, and the relation is that whenever you have such an operator p here, the p applied to f is just this expression there in the module. Okay, so this is in terms of the algebra with the two derivatives. But in what follows, we'll do most of the calculations, most of the considerations in terms of this simpler or smaller algebra that is only generated by dx. So it's a subalgebra. And at least for the talk, I will do this hypothesis on the function I want to integrate. That, okay, so it's supposed to be D-Finite with respect to A, and maybe I've not insisted on that. So D-Finiteness is really relative to some framework of operators, so to some algebra. So here we need f to be D-Finite with respect to t and x. And being D-Finite means I will have a dimension that I will call d for this rational function, this vector space over the rational functions, that is of this module when viewed as a vector space. And the hypothesis that we do without in the, or the hypothesis is that there is an H in the module that we call cyclic, in the sense that this subalgebra S applied to H is enough to get the whole module generated by F. But the interest of this notion here is that this H makes it possible to write every object just using this derivative and not necessarily using the two derivatives there. Okay, and now, so to say, for any element in the module generated by F and G, there is some operator using dx only, some AG, that gets you from H to G. So you can view now AG, or its coefficients, that are rational functions here, along the powers of dx, as a first way to parametrize, elements in M sub F. Good. Okay, and now in those terms, what is the creative telescoping that I want to present? It's given F. We want to find a telescoper T, and it's always like this. It's only derivations in T and only rational functions in S. So it's something even smaller than in S. And the certificate, so those algorithms look for certificates in the module generated by F, such that we have this relation here. And if you think of it, what it really does is that internally what it does is that it computes this intersection. That is, we want to find those operators applied to F that can also be expressed as a derivative in X of some element of the module. Okay. And the other technical notion or technical object that we need to perform the algorithm is something that is expressed in terms of duals of operators. So just syntactically, let me start syntactically, the dual, you can view it as that when you're given an operator in just dx here, so someone in S, the dual is what you obtain by exchanging the order and changing the sign of d. When you pass from here to there, the dx becomes minus dx and goes to the left. And it's related to integration by part. And I need this to write this so-called Lagrange identity that whenever you're given when you're given a P, there is something that we don't really need to, for which we don't really need to know a formula, although I did one, such that for any two functions, but I will U and H, you have such a formula. That is, you can apply P to H and compare this to what you get when you apply P star to U. And you have this comparison modulo a derivative with regard to X. Just in what follows, I'll only use U, a rational function, and H, someone in the module. Okay, if you want to prove that, you can do an induction and show this formula, or in the way you like. For what follows, we really don't need to know this formula, as the way I'm presenting it is that we throw away anything that is a derivative with regard to X. So we just need to know there exists. Okay. And now, now let's use this Lagrange identity to go to an algorithm. Okay, so I've repeated this Lagrange identity, and again, H is cyclic, and I'm given an L in the algebra using only dx that kills this H. And I will use this Lagrange identity in two different ways to simplify the writing of an element in the module. Okay, what is written here? Okay, so the first reduction is that in the algorithm I need to work with an element of the module AF, which really I can write using the cyclic element using only one derivative, not two. And now this information has several rational functions as coefficients. And there's a way to go back to one single rational function. And it's the first use of a Lagrange identity. That is, given G in even G there, that is given by, therefore, A sub G, that is the operator that obtains G from H. Then, by setting U as 1 and P is A sub G, I get this, that the G, instead of being A sub G times H, is written in terms of H times a rational function obtained from the dual of A sub G, plus some derivative that I won't consider. Okay, so again, several rational function coefficients to 1. And now we want to go further with the goal of obtaining a reduction to something more reduced. Is this A star sub G of 1 the only possible rational function that describes G modulo derivatives? No. By another choice, that's doing P is L, which gives this. We have natural derivatives in X that are all those guys that can be written like this. That is, you consider any U, any rational function. That is, if you consider the image of the dual of P, of the rational functions under the action of the dual of P, all those guys are derivatives. So you can shift this A star G of 1 by any such P star of U. This is what is written in symbols here. So the same G, for any U that you may want to choose, is modulo a derivative, a multiple of H by a rational function, and you have this freedom here. So this is fixed, and this can move. And now, now there's a proof that if you manage to start with some G and have this go to 0, then this makes G a derivative with regard to X, and it's a test actually. That is, we have this equivalence that G is a derivative if and only if there is a rational function that makes this relation here. And it's important to have such a test because remember, the G here, remember from the method, we will try to recombine several derivatives with regard to T of F such that the linear combination falls in the derivatives of the module. So we'll use this as a test to test that G, that the linear combination we produce is right. Okay, now this was just speaking, and now the natural questions are, how can I make this into a reduction? That is, how can I choose the right use that reduce, simplify, make this here small? Okay, and this will lead to another. And okay, so I will show what happens on this example. So again, the data, again this the equations that we had, but now written as operator. And now this 1 and d sub x are my basis elements. But you can view them as so 1 plus the ideal and dx plus the ideal are two classes in the quotient of the algebra annihilating ideal of the function to be integrated. And all those monomials here, dn, dp, dx squared, and all their multiples can be reduced down to 1 dx modulo rational function recombination. Okay, now what our problem is to find, it was almost like this, but now it's in operator notation, which means we want such a relation modulo the left ideal generated by those non-commutative. Okay, and okay, in this case, H can be chosen to be F, so that the L, which was the P, so no, the L can be chosen to be the second order operator. Again, this picture, and now what is the idea of the algorithm? So for successive monomials, the p's that are in this plane here, for successive blue monomials, which we choose to consider in increasing order, where increasing means, for example, by total degree, or in fact, going up in a monomial ordering. Okay, so the G that we consider, the G's of the previous slides, sorry, back to here, the G is here. So we instantiate this for those blue monomials. So when G is such a P applied to H, and H is F, in our case, the AG is simply computed. It has, for each of those, we can compute two rational functions such that we have this relation here. And we follow the steps that we reduce from two rational function coefficients to a single one by using Lagrange formula once. And the rational function is just this one, u minus derivative of v. G can be written like this. And for those there, we do the analysis by hand. That is, all those guys here that you can compute concretely, these are rational functions that, in fact, are just polynomials in X of degree not more than 3. So our goal is to reduce, to simplify those polynomials. And the observation is that if you consider images under L star of those monomials here, X and X to the 1, with proper renormalizations with those p's, you can get X cubed, you can get X squared. So that modulo the image of L star, you can reduce further the expression here down to polynomials of degree at most 1 in X. Degrees at most 1 in X. And okay, and this is the confinement. That is, we are now confined in dimension 2. So with a proper linear algebra between those normal forms of the blue blobs, we get relations. That is, these expressions are just derivatives in X, with here something that has been recombined to 0. Sorry. And these were the same operators for the integral as those that we had by other methods. And now, I think I have 5 more minutes speaking.
5 minutes.
And now the most technical techniques of the technique. Okay, so how do we do to get, what remains to be done is to understand how you can reduce, you have to understand the image of all rational functions under this L star. And the way to do that is to consider local decompositions of the rational functions. So here is a rational function R that we want to reduce. We write it with the polynomial part, it's a traditional polynomial part, and sums like this. I mean, a sum of objects like this. That's we isolate the poles. It's pole alpha. And now what we do is that, okay, this, remember, L is very concrete in the algorithm. It's the input. It's known data. So L star, you can compute it. So you can do this symbolic computation of L star at such monomials here, so that you understand the local behavior of it in this form. That is, from a pool of order S, it's shifted. So to understand this, maybe you need to compare this to the case of Hermite reduction, where this here is just derivative with regard to X. So in this Hermite case, usual Hermite case, what you would have is that here you would have minus S, and here minus S minus 1. So this generalizes to another operator with another shift, sigma. And here is something that we want to call an initial polynomial. that is generally not 0 and occasionally 0 at an integer. And you have the same thing at infinity. Okay, so this was the analysis, and suppose you want to simplify such an R, you want to be able to target a given exponent here. So I've just shifted S by sigma, so that if I want to cancel such a term in an R, I know I have to use something of this kind. Just the only trouble is that this may be 0. So what if you want to kill such a term in R, you would want to use that. It's okay unless this inverse is not defined. So now we have this. We now have a reduction strategy, which before we read that, we want to compare to the Hermite case. The Hermite case, remember, is that you have a reduction down to the pools of order 1, which you cannot reduce, and which you consider as an obstruction to existence of a rational integral. It's the same, except that the obstructions are not necessarily at exponent -1. They are precisely at the zeros, and the exponent that are zeros of these initial polynomials here. So we have a strategy that is, we start from an R, and also as opposed to the Hermite traditional case, we don't start by reducing the infinite this polynomial part. We reduce at the finite alphas first. We reduce, and we need to skip what remains as an obstruction. And in the end, we reduce the part at infinity. So in this process, we've reduced, and what remains are only a few finitely many monomials related to the zero set of the initial polynomials. And what is this? And okay, so probably there's a proof that okay, time is running out of time. Okay, but we prove that this reduces. And this has been implemented, and fortunately enough, we find the same expressions as by the other method. Oh, where is that? Yeah. Okay, the same example, it was in less time even, so it's some improvement. Okay, so we've also run the method over a large set of integrals to find that. So it can be better than what we had, and there are cases that we still don't understand with white phase, and for reasons that still need to be investigated. That is, our algorithm relies on bugs that maybe not ours, that rely on other tasks. But on the theoretical side, it may be that passing from P to P star introduces a lot of apparent singularities that the new approach has to face, has to cope with, and it's still under investigation. We don't understand really. Okay, so I want to finish with this summary of the 3 layers of ideas, algorithmic ideas. So in the 90s, the approach was by solving an auxiliary equation. I mentioned Abramov's decision solver. And I want to compare a primal reduction-based approach to dual reduction-based approach. The primal is that you attack the function itself, and the dual is that you reduce the coefficients. And I thank you for your attention.
Are there any questions, comments?
It was planned, yes, it was planned. That is, we have this ng fund that already contains my code and Salvy's code, and this has to go there.
Any other questions?
So your cyclic vector, as in H it was called, if I understand correctly, in practice you would usually take 1 for that.
Often.
And L is the operator that annihilates your function. Do you have natural examples where you would like to choose a different cyclic vector?
Well, okay, so this H is F, right? 1 applied to F.
Yes.
Okay. So it's, I don't know if there are examples where we would like to. I cannot say. I can think of an example where we expect another H to go faster than F. It's rather the opposite, that in cases where we observe that the data is that F is not cyclic, we need to change by some random change of variables, and typically it creates additional calculations there.
But if F is not cyclic, this means you don't have the minimal annihilator? Or?
No, it means that the variable x is such that the ideal, the stairs cannot be put into this shape position, shape lemma position. Okay. It's not sufficiently studied.
Okay, let's thank the speaker again, and we continue in 2 minutes.